We have just learned how to solve simple inequalities, but in this video, we'll take a look at compound inequalities. So what exactly is the difference? Take a look at example 6. The inequalities that you see there are compound inequalities. That is, they are three-part inequalities. Notice you've got two inequality signs, which divides this into three different sections or three different regions. So to solve a compound inequality, our goal is to isolate the variable not on one side, but in the middle. So whatever operations we need to do to get the variable by itself in the middle, we're going to apply those operations to all three parts of the inequality. So let's give this a try on example 6. Solve the following inequalities, and as we've been doing, our goal is to express the solution in interval notation. So my goal is to get m by itself in the middle. Now, if this were just a two-part inequality, maybe you can cover up one side of the inequality. To solve that inequality, we would begin by adding 5 to both sides. Well, we're going to do that same thing and just be sure to apply it to all three parts. So I'm going to add 5 to the middle and then also on the other two sections as well. Then we'll simplify all three sections. On the leftmost region, we have -2 plus 5. That gives us 3, less than or equal to. In the middle, now we just have 2m. And on the right side, 2 plus 5 gives us 7. Again, keep your eyes on the middle region. Our goal is to get m by itself. So to do that, we need to divide by 2. And whatever we do to the middle, we have to do to all three parts simultaneously. So we end up with the compound inequality, 3 over 2 is less than or equal to m is less than 7 over 2. Now remember, it's fine to keep your fractions in improper form as long as they are reduced. That's the solution to the inequality, but I want to convert that to interval notation. Before I get to interval notation, I'm going to envision it on the graph. So 3/2, which is about 1.5, is on this side. So maybe 1 is here, 2 is here. Down the number line, we encounter 7 over 2. That's about 3.5. So between 3 and 4, we would have 7 over 2. So we want to shade all of the numbers between 3/2 and 7 over 2. And then notice our inequalities are different. So the inequality closest to 3 over 2 is an inclusive inequality. So I'd use a solid point there. Closest to 7 over 2 is a strict inequality, so I would use an open circle there. And then we can, from the graph, translate that into interval notation. On the leftmost part of our graph, we have 3 over 2. Because it has a solid endpoint, we're going to use a square bracket in interval notation. And then the rightmost value is 7 over 2. And because of the open circle or the strict inequality there, we're going to use a parenthesis. So to understand what this interval notation means, we can take any number between 3/2 and 7/2, plug it into the original inequality, and get a true statement. We need to recognize 3/2 is a solution. It is included in the solution set because of the bracket there, but 7/2 is not included in the solution set. Okay, let's try that coordination of three regions again on the next example. And do notice the next example has a fraction. Our goal is the same. We want to get x by itself in the middle. So the first thing I would do would be to clear the fraction. So let's multiply all three parts by 2. I'm just going to sneak it in there on the original equation. So on the left side, we'd end up with -2. In the middle, the denominator cancels. That leaves behind 3 minus x and 10 on the right side. Our goal is to get x by itself in the middle, so the next thing we need to do is subtract 3, and we're going to do that from all three parts. This leads us to -5 less than -x less than 7. To finish off, we need to clear the variable's coefficient, so I'm going to divide all three parts by -1. Okay, I hope you have alarm bells going off on your head because I'm applying a negative to all three parts of this inequality. Remember, if you multiply or divide by a negative, you have to reverse the direction of the inequality. So in this case, we're going to reverse both inequalities. I'm going to circle them to make sure I carry that plan out. So simplifying here, -5 divided by -1 is +5. I'm going to switch from less than to greater than. In the middle, we have just x. I'm going to switch this one from less than to greater than, and we have -7. So technically, we have a correct solution here, but this statement, we could say it's mathematically impolite. Most of the time, when we talk about inequalities, we want it to go from smallest to largest. Just like we read our language consistently from the left to the right, when we look at a number line, the numbers are always in order from left to right. So we like things to go from smallest to largest. What makes this solution a little bit awkward is that our smallest number is over here on the right side. So what I'm going to do is pick up the entire inequality, flip it around, and then set it back down. So I'm going to take that -7 and make that the left side because that's my smallest number. And do observe here, the point of my inequality is towards the -7, so I'm going to keep that to be true. The point is going towards the -7. X is in the middle, and then again, notice this inequality, the big side is facing the 5, so I'm going to make sure the big side is facing the 5. So those two statements are equivalent, but this one is mathematically polite because it goes from smallest to largest. Okay, let's take a look at what this looks like on a number line. So our two most important numbers here would be the -7 and the 5. And we're going to shade all the numbers in between -7 and 5. Both of those numbers use strict inequalities, so we can use open circles on our graph. And then finally, in interval notation, our leftmost value is -7 with the parenthesis, rightmost value is 5 with the parenthesis. So this is interval notation. Now it almost looks like an ordered pair, xy ordered pair, but we have to remember it's going from x equals -7 to x equals 5. Also observe only the numbers in this blue shaded region are solutions, but the endpoints are not included in the solution set. So solving a compound inequality, remember, whatever you do to isolate the variable in the middle, apply to all three regions of that inequality. Now, what might this look like in an application setting? Let's talk about construction. The perimeter of a rectangular fence is to be at least 100 feet and no more than 180 feet. Okay, so we're going to build a fence. I want to draw a picture. There's my fence that I'm going to be building. And we want to make sure that the perimeter is at least 100 and no more than 180 feet. Perhaps this is like real life and you have a limited amount of materials, but you've got some possibilities, right? Between 100 feet and no more than 180 feet. So our perimeter has to be between those values, at least 100, so 100 or more for our perimeter, but no more than 180. So it has to be 180 or less. So we want to make sure the perimeter is in between those two values. If the width of the fence is 22 feet, so I'm going to label that over here. The width of my fence is 22 feet. What is the range of values for the length of the fence? So we'll call this dimension the length of the fence. And focus your attention on the last part of your word problem. What range of values for the length of the fence? We're trying to figure out how can I set the length. Now, to help us understand possibilities, the width has to be fixed at 22 feet, but perhaps the length could be longer than the one that we have drawn, or with a fixed width of 22 feet, maybe the length is a little bit smaller. So we want to know, how can I set the length so that the perimeter of these possibilities is between and including 100 and 180 feet? Now, the good thing about this is we already basically have our model. This is our plan right here. We're going to trap that perimeter between 100 and 180 feet. But let's put more detail in for the perimeter. So the smallest possible value is 100. Let's calculate the perimeter of our rectangle. Hopefully you recall that perimeter is twice the width, 2 times 22, plus twice the length. We're just going to call that 2L there in the middle. Okay, 2 times the width plus 2 times the length. This gives us a compound inequality that we can solve. Our goal is to get the variable by itself in the middle. I'm going to go ahead and multiply 2 times 22 there to get 44. And then I'm spying that L in the middle. My goal is to isolate it in the middle. So let's begin by subtracting 44 to all 3 parts. 100 minus 44 on the left gives us 56. We have a 2L in the middle. And 180 minus 44 on the right, that's going to give us 136. And then we'll go through and divide all 3 parts by 2 to clear the variable's coefficient. And we'll end up with 56 divided by 2 is 28. We have our length isolated in the middle, and 136 divided by 2 gives us 68. So that's our range of possible values for the length of the rectangle, keeping the width fixed at 22 feet and staying within the range of resources that we have. So we can say the length of the rectangle must be between. Now, I want to communicate the idea that we're using an inclusive inequality here, so I'm going to say between and including. So between would be not including 28 and 68, but because we have inclusive inequalities, we want to make sure that's part of our solution. So the length of the rectangle must be between and including 28 feet and 68 feet. Make sure you always include your units when you're solving an application problem. Okay, so solving compound inequalities, your goal is to isolate the variable in the middle.